Okay, let's wait another 10 seconds. Okay, here. Okay, good morning, everyone. Hope you can hear me. Okay, so let's move on with our kinetic systems here. The last thing that I was talking about after we finished talking about the basic theory behind chemical kinetics. Now we really want to understand a little bit the structure, okay, of kinetic systems in combustion, which is not at all easy, okay. There can be very, very complicated chemical kinetic mechanisms. I showed you a typical one last time. So I wanted to concentrate on two prototypical systems here, a very simple reversible reaction, okay, and so-called consecutive reactions. Let's concentrate on this first, okay, the reversible reaction. I would like to make a little link between kinetics, okay, and an equilibrium again, and you'll see that there is a very sort of logical link between the two. Okay, so we have everything that we need to treat this kind of system here. If we remember that in general, okay, this is what you always have to apply, okay, which is your rate of change of the molar concentration, okay. You just multiply by the difference of the stoichiometric coefficients for this species times the reaction rate, and the reaction rate is essentially the forward reaction, okay, minus the backward reaction, okay. So it's a reaction constant Kf, the product of the concentrations, okay, minus that would be obviously single prime, and K backwards times the product of the concentrations, okay? It's actually more difficult to write it in this form than to actually apply it, okay? So let's apply it to this very simple reversible reaction system. So we have that the rate of change of the molar concentration of A, okay, is nothing else. Well, we could do it the really long way. So for A, it's 0 minus 1, okay, times essentially the forward rate, omega f, minus the backward rate, okay? And this is simply 0 minus 1 Kf forward rate constant times A minus the backward rate constant times, okay, the concentration of B. Okay, so very simply put, this would be minus Kf of A plus Kf of B, okay? Now, you'll be able to very soon to just write this immediately because by just looking at it, okay? So the rate of change of A, well, will be equal to the reaction going from left to right, okay? Depletes A, so you have to multiply Kf by A, and of course there is a minus sign because this means that going from left to right kind of decreases A, and the opposite is true for the other direction reaction, okay, from B to A. It increases, so you have a plus sign, okay? And again, dB by dt will be equal to, well, it's essentially the opposite in this case with the opposite signs, okay? Okay, and this is our system of ordinary differential equations that will determine the time evolution of our system, okay? The system, again, let me write it here. It's a reversible reaction where you have a forward process and a backward process, okay? Now, how do we treat these systems? Well, we know that we can write many things here. For example, the progress variable here. We know exactly how to write it. Okay, so it's the number of moles of A minus the initial number of moles divided by 0 minus 1. Okay, and that's equal to the number of moles of B minus the initial number of moles of B divided by 1 minus 0. And so if we divide by the volume, the number of moles divided by the volume will be equal to what? The molar concentration, okay? So what we have here essentially is, with a minus sign here, the molar concentration of A minus the initial molar concentration of A, we can write it like this, is equal to B minus the initial concentration, okay? So I can put it up here or down here, the initial concentration, okay? So one thing that we figure out immediately is that A and B are not independent, okay? Because you can write down the concentration of B simply as A0 minus A, okay, plus B0, okay? So you see that from here, you understand that A and B are the function of the other. So in fact, by going up here to the ODE that regulates the evolution of A, we can rewrite the ordinary differential equation for A by substituting now the expression for B, okay? So here it is, okay? It's more complicated than it actually is. It seems more complicated than it actually is, okay? You can still hear me, right?
Yes, Professor.
No.
Okay. So we can regroup, for example, the variables here so that you have, for example, minus Kf plus Kb multiplying A, okay? And then a bunch of constants here, Kb multiplying A0 plus B0, okay?
Professore, scusi, posso fare una domanda?
Prego, prego.
Perché in questo caso abbiamo scritto KF e KB, mentre prima abbiamo usato sempre KF, quando abbiamo scritto la variazione della concentrazione di B, per esempio?
Scusi, perché mi sono sbagliato, ovviamente.
Ah,
Che dice?
non vedo il cursore. Quando scriviamo variazione di concentrazione di B...
Non vede il cursore, mi sta dicendo? È preoccupante.
Sì, ecco, ora lo vedo. Sì, sì.
Okay. Sì, no. He was asking me why did I use KF here, because it's a mistake. Here, okay? So obviously for the backward reaction, you have to use KB. So here, I hope you can see the cursor because you said that you can't see it.
Sì, si è un attimo bloccato lo schermo.
Okay.
Allora, tutto bene.
Yeah, sorry about that. Okay. Yeah, you have to be careful. I mean, otherwise we're gonna. So don't do like me. Anyway, I'm gonna have to. Yeah, this thing doesn't move anymore, so I'm gonna have to clear it very soon. So, well, this is an ordinary differential equation, right? Which is linear. I hope you can see that it's a linear ODE. Okay, linear ODEs. We're going to talk quite in detail about linear ordinary differential equations. I think by the last year of engineering, you really have to master this concept of linear ordinary differential equations. Not that you have to know the solution for every single case, okay? In this particular case, we have a constant here, so it's not immediately clear how you would have to solve this. But it is important to understand, to know not only just the solution, the analytical solution to linear ordinary differential equations, which is one of the very rare cases where you can actually write down an analytical solution for a differential equation, okay? But you also have to interpret it, okay? And we will, in terms of time scale. So we're going to look quite in detail, okay, about these linear ordinary differential equations. And you'll see that we can have a geometrical representation of them that you probably have not seen yet, okay? And we will use this as a blueprint, let's say, even for nonlinear systems, okay? But one thing at a time. So it's a linear system. We can write down an analytical solution. So I'm going to write it down for you. You know that it will involve exponentials, obviously. We don't have to know exactly why this is the solution, but you can prove it by just differentiating it with respect to time. But in any case, it would be the following, okay? So we write down the concentration as a function of time, okay? So we can use this notation here. This will be equal to, okay, we have a constant multiplication here. So A0 plus B0. Then we have the term KB over KF plus KB, okay? Then 1 minus the exponential, okay? Again, it's not necessarily important that we know how to write it down. Okay, so exponential of minus kf plus kb to the t, okay? And then we have another term which is a0 and the exponential of minus kf plus kb to the t, okay? So if you don't believe it, just differentiate this with respect to time and you will get exactly this term here, okay? Where a is this function here. Now, why is this, why do we care, okay, to write down this in full? Well, remember what we have, okay? We have a reversible reaction between A and B with KF and KB, okay? Now, one thing that we can do now is we can say, what about KF and KB, okay? What, in what relationship, okay, are they, okay? For example, we can hypothesize, okay, that KF, in fact, is much smaller than KB. Okay, this is our first hypothesis. Okay? What happens if KF is much smaller than KB? You can even imagine this by writing down a very big arrow going backwards and a small arrow going forwards, okay? So KF is small and KB is much larger, okay? Now, this is a dynamic kind of process where the rate, the forward rate, we expect it to be less than the backward rate, okay? So do we expect at equilibrium this reaction to be shifted to the right or to the left? Well, intuitively, we expect it to be shifted to the left. In fact, we can write down, we can look at this full expression here for A. When I move, can I ask you a question? When I move the cursor, you can see it moving, right? Hopefully. It's a question for the students. Can you hear me?
Io personalmente ora non lo vedo proprio il cursore.
Okay, so when I say this and that, you will not understand what I'm saying,
No,
right?
prof. We do
eh?
not. No, prof.
But you can
Sometimes
see the
we
dot.
see, sometimes not.
You can see the little dot, right? I mean, this dot here.
No.
Yeah, yes.
Sì, sì.
Okay.
No.
So does any of you know how to understand? Well, no, it's a pity because I'm pointing stuff and you don't know that I'm pointing. So what I'm going to do is I'm going to draw little dots like this, okay? Hopefully. Anyway. So let's look at this expression here for A, okay? Now, what happens if we have KF much smaller than KB? Well, look at, for example, this term here, okay? This term here. Well, KF is negligible, so you have 1 here. So AT would be essentially A0 plus B0. All right. Okay. Times 1. Okay. Then within the brackets, you simply have 1 minus E to the minus KB. Okay. And similarly here, E to the minus KB, right? Because we have neglected KF with respect to KB. So we can write down an expression for A, which at the end of the day is simply the initial value plus B0 1 minus E to the minus KBT. Okay? So what do we learn from this? Well, a very straightforward thing that suppose we start from initially from B0, 0 or very close to 0, okay? Then obviously what we learn from this expression here is that A, okay, will be essentially very close to A0. So let me just do this graphically, okay, over here. If this is time, okay, we can have, for example, the value of A0 over here. What's going to happen is A will decrease a little bit. As you can see, there is a 1 minus. So, but it will stay very close to A0. Okay. And what about B? So this is AT. Well, it will increase slightly, but it will stay very close to B0. Okay. So this, for example, if B0 is 0, okay, then B will be very close to the initial value. So you see what happens here. If you start from A0, the final at a very long time, the final composition, okay, is going to be very close to the initial composition. So essentially, you see here, we have a situation where the reaction is predominantly shifted towards the left, towards A0. Sorry, towards A, right? Now, obviously, you can do exactly the opposite, and you can think of essentially KF being much larger than KB. Okay, the forward process being faster, so we can sort of schematically represent this with a larger arrow to the right. Okay, and so let's now take the. You should go back to the overall solution, which is this one here. Where is it? Okay, over here. And you'll see immediately that A, okay, because KF, okay, in this case is much larger than KB, you can see that this ratio is essentially goes to 0, and we're only left with this bit here, A0 e to the minus KFT, okay? And obviously, this is a term which will tend to 0, okay, with a rate which is proportional to KF. On the other hand, B, okay, which is equal to, again, they're related, so remember, it's equal to A0 minus A plus B0. This is, you can rewrite it using the expression we just wrote for A as A01 minus E to the minus KFT. Okay, so you see that essentially for long times at t going to infinity, A goes to 0, and essentially B will tend to A0. Okay, so the situation that you have here is rather the opposite of what we've seen before. Again, this is t. This is your initial value of A0, okay? So you see that B now will tend to A0 like this. B of t, okay? And A will tend to 0. So you see that eventually at equilibrium, we have that the reaction is completely shifted towards B, towards the right, okay? Okay? Very good. So essentially, we have linked the size of the forward and backward rates here to whether the reaction is shifted to the right or to the left. Okay? Now, what about at equilibrium? Well, at equilibrium, okay, what happens? Well, we know that the rate of change will be 0, right? So, for example, the rate of change of A, okay, will be, well, we said it was minus KFA plus KBB. Well, this will be identically equal to 0, clearly, because we're at equilibrium and A doesn't change anymore, okay? So as we usually do, and we did also last time, we can relate the ratio of the forward to the backward rate, okay, to the equilibrium constant in terms of the molar concentrations, okay? And from this relation here, this would be equal to B, okay, the concentration of B at equilibrium. So we have like this subscript here to remind ourselves that these are the concentrations at equilibrium and obviously at A of equilibrium, okay? And also because B is a function of A, we can write down the following, okay? Divided by A of equilibrium, okay? So what can we do with this reaction? Well, we can relate now the, if this thing moves up, do me a favor. Okay, as soon as I finish with these, then I'll clear this blackboard, okay? So we can relate, for example, the composition of equilibrium of A, okay? A of equilibrium with the equilibrium constant, Kc. Because all we have to do now is just solve for A of equilibrium. Okay, and we have here Kc plus 1. Okay, 1 over Kc plus 1. Okay, now why is this important? In fact, if B 0, as we usually do, because this is a reversible reaction, okay, so suppose we only start with A, okay, you could even write down simply A0 Kc plus 1, okay, if B initially is 0, okay? So you see that for Kc tending to 0, okay, so the equilibrium constant going to 0, the equilibrium concentration of A, okay, tends to simply A0, okay? So what does that mean? It means that the reaction is completely shifted towards A, towards the left, okay? Shifted towards the left. And this we knew from chemical equilibrium, if you remember. Now, if Kc, on the other hand, is very large and tends to infinity, very, very simply, A of equilibrium will tend to 0, okay? So this will just essentially be shifted towards B, okay, where A is all depleted, so all the way to the right, okay? You can see this in terms, just playing around with these things once again, you can see this in terms of the progress variable as well. It's rather easy to see. If I can shift this, okay. So remember that we wrote the progress variable as Na minus Na0. And then this was 0 minus 1. So if we divide by the volume, okay, this would be essentially minus A minus A0, right? And that's obviously also true at equilibrium. So I'm going to write down the subscript equilibrium here. So we have essentially A0 minus A of equilibrium, okay? And if we substitute now the expression for A of equilibrium, okay, we essentially have A0 multiplying 1 minus 1 over Kc plus 1, okay, which is simply A0 Kc over Kc plus 1. So this is essentially the progress variable, okay, at equilibrium. So clearly, this would be for Kc going to 0, okay, the equilibrium value of the progress variable will tend to 0, as so completely shifted to the left, as we said. And if Kc goes to very high, so to infinity, for example, here this would be 1. This factor here would be 1, and we have C of equilibrium going, tending to 1, okay? Rather straightforward, okay? And that's for consecutive reactions. So we can sort of do all sorts of links, okay, between the concepts that we know in chemical equilibrium and now the new concepts of chemical kinetics, okay? Now, obviously, reversible reactions are all over the place, okay? Not just in combustion, clearly. But I would like to now talk about the second kind of chemical mechanism, which is the consecutive reaction, okay, mechanism. So if you have finished copying here, I would like to clear the... Are you done?
Yes, Prof.
Okay. To clear this canvas because when it gets too crowded, I can't move it. I can't move it around anymore. Well, yeah. Ah, okay, fine. Very good. Now, let's look at, and you can still not see my cursor moving around, right? Say yes or no.
Yes, Prof.
Now you can.
No, we can't.
Oh, you can't. Can you just give me 1 second? Do you know if there is a way of actually... You know maybe what is going on here? I'm only sharing, I know what's going on. Wait a minute. I'm sharing the full... Give me a second here. Can you now see the...
No, Prof. Same as before.
Are you kidding me?
No, Prof.
Ma com'è possibile?
Prof, io
now
credo che lei dovrebbe condividere, non so se sta usando una tavoletta.
Sì.
Probabilmente si dovrebbe condividere direttamente la tavoletta.
No, io ho fatto tutte e due. Prima stavo condividendo la tavoletta e basta. Adesso sto condividendo tutto lo schermo.
Allora, professore, ci sarà forse un'impostazione di questo Microsoft Whiteboard.
Vabbè, ok, whatever. We tried.
Thank you.
I'm not very lucky, as you can see, with these devices. Anyway, so we wanted to see consecutive, okay, reactions. Okay, now consecutive reaction, well, an extremely simplified case of a consecutive reaction is the following. As you can see, okay, there is a consecutive process here because you can't get to C, okay, if you don't first produce this intermediate species B. So you start from a reactant, you produce an intermediate species B, and then you can finally produce your product, let's say C. So we can write down K1 and K2 as the two reaction constants, okay? Now, this is much more sort of similar to what is going on in combustion processes, okay? Which, as I said, they're very complicated. But if we are to extremely simplify things, okay, you will have essentially a fuel, okay, a product, sorry, a reactant. You will have a final product, okay, which is probably CO2 or an H2O. And then a series of intermediate species here, which we call in this particular case B, okay? But they can be referred to as, well, intermediate species, okay? But in combustion, we can also call them as radical species. Again, the fact that we have a radical here as it indicates the fact that usually they are intermediate species that are stripped, okay, of their covalent bonds, okay? So imagine, for example, the molecule of CH4, okay? This molecule can be stripped, okay, of one hydrogen atom, okay? So we can sort of write it here as CH3 and then a dot here, which indicates a free covalent bond or a free sort of electron that can be, and H is exactly the same, okay? And you can go on, you can have CH2 and so on, okay? This, in fact, is the very first sort of step, okay, in the combustion of methane, where you have essentially the process of oxidation of the carbon atom. Eventually we'll get to CO2 somehow, especially from CO, but we will have, in order to get to here, we will have to strip CH4 of all the hydrogen atoms, okay? So you can see that there is a bunch. So this is our species A, if you will, and this is our species C, okay, which is our final product. Of course, C is not carbon. C is the final species. But all those intermediates, okay, will be referred to as B, okay? Will be referred to as these radical or intermediate species, okay? In fact, sometimes we refer to as the radical pool to underline the fact that we have a lot of those intermediate species. In this case, we all group them up, okay, symbolically with B. Okay, so it doesn't. You cannot simplify any further. Okay, this is really the skeletal, okay, structure of what a combustion reaction will be. Now, for those reactions, we can now write down very easily our ordinary differential equation system. Okay, for A, it will be nothing else but minus K1A. Okay, and for our intermediate species, okay, it will simply be K1A minus K2B. Okay, as you can see, neither A nor B, okay, is dependent on the product C. Okay, so we can actually neglect writing down C anyhow. Okay, it would be a third reaction. It would be a third ordinary differential equation, which is a function of the other two. So we'll just concentrate on this two-dimensional system, A and B. In particular, this is straightforward to solve because this is fully linear. So by just looking at it, we can solve it. So the A of t is the initial condition, okay? And then an exponential e to the minus k1t, okay? What about B? Well, we can write it as the solution of A, so K1, A0, e to the minus K1t, okay, minus K2b. Now, you see it has two terms, okay? these two terms here. One is positive, okay? The other one is negative, okay? So we foresee for the behavior of B, okay, an increasing, decreasing behavior, okay, because we have a forcing term here, which is positive, that will cause an increase of B, and here a forcing term that will cause a decrease of B, okay? In fact, if you solve it, okay, I will just write down the final solution, okay? It's not easy to verify that B is essentially A0. This term K1 over K2 minus K1, and then e to the minus K1 t minus e to the minus K2 t, okay? I would like to also underline a very important thing, okay? Well, look at the units here, both for K1 and for K2, okay? You see that, well, the dA by dt is essentially molar concentration per unit time. So on the right, you have a molar concentration, okay? And so K is 1 over time. So both K1 and K2, in fact, okay, have dimensions of 1 over seconds, okay? 1 over seconds. So in fact, the reciprocal of 1 over K1 and 1 over K2 are what we call time scales. They are representative of 2 different times. And you have, in fact, that B, okay, contains both of them, okay? Both of these scales, okay? Now, this will be a crucial, okay, aspect of combustion reactions, okay? And the reason why we're actually concentrating on this consecutive reaction system, okay? Usually, you will have reactions of the kind A going to B, okay, that are very fast, okay? So very, very fast, we're going to have the production of a pool of radicals B, which then, according to the second reaction, more slowly, okay, will oxidize to form your final product, C. So in fact, a typical case or scenario is that K1 is always much larger than K2, okay? This will also mean essentially that 1 over K1 is much smaller than 1 over K2, meaning essentially that the time scale associated to the first reaction, okay, A going to B, is much smaller, much shorter than the time scale characterizing the second reaction of oxidation from B to C, okay? So if we are to draw now the solutions as a function of time, okay, what do we have? Well, let's look at the evolution of A, okay? We start from A0, and we have an exponential decay with time scale K1, which is a fast time scale, okay? 1 over K1 is in fact, very fast. So we have this kind of situation where you have a rapid decay of A to 0, okay? Now, in fact, you can prove it very, very easily here. If you take the slope, okay, of will try to do this. But if you take the slope at t equals 0, okay, this will intercept the x-axis here at 1 over k1. Sorry, this is not order. So we can actually, okay, write down that this time scale here, from here to here, is actually the fast time scale. Okay, we can actually have a little line here to sort of highlight the fact that we have a temporal, very fast time scale, okay, from here to here, where the reactant A is fully depleted, okay? Now, let's concentrate on B, okay, for a second here. And look at the form of the expression for B. Now, we're looking for the behavior of B for large times, okay? So for T very large, okay, you see that you have here 1 and 2 terms that are exponentials. But we know that the exponential with the K1, okay, will decay much faster, okay? So if in fact we substitute the fact that K1 is much smaller than K2, we have that the exponential behavior is essentially B equal to A0 and then E to the minus K2 T. Why? Look at this group here. I'm going to mess up this whole thing because now you can't see clearly the arrow, so you can hear me, however, right? I mean, I really have to check, otherwise.
Yes, Professor.
Okay, so if you look at this term here and you substitute the fact that K1 is much smaller than K2, okay, and the fact that this is essentially, sorry, it's the opposite. Sorry, it's obviously the opposite. Obviously, K1 is much bigger than K2 here. It's 1 over K1 that's smaller than K2. So the time scale associated to K1 is clearly smaller than the one associated to K2, but clearly K1 is much bigger than K2.
Quindi nella formula della concentrazione di B c'è E alla meno K1, non K2.
No, un attimo. No, cioè sono tutte e due, K1 e K2.
No, nella seconda semplificata, quando noi pensiamo che...
No, chiaramente c'è K2, perché adesso perché K1 minus
giusto,
K1
perché va
is
più
much,
velocemente a 0, certo.
Certo.
Okay.
So this will very rapidly go to 0, okay? This term here will be minus 1, okay? And so this is what you have, okay? Eventually, you have this situation here. So we can draw, okay, this asymptotic behavior, A0 e to the minus K2 T, okay? Now, let me just try and, okay? So now we're going to have to draw the profile for B, okay? Now, clearly, this expression here that we just wrote, okay, is the overall. So there is an increasing and decreasing term. So in fact, B will start from 0, okay? It will increase within the very fast time scale, but then it will be constrained to this behavior here, okay? And it will decay much. Sorry, I'm just trying to follow. I'm just trying to follow this. Okay, I mean, I hope you realize that I'm having difficulties, okay? If you take the tangent here, it's very easy to prove that essentially this is going to be essentially 1 over K2, okay? So again, this is B, okay? This is A, okay? And this is the situation, okay? Now, the situation highlights a very important aspect here. We have 2 consecutive reactions, the first one being much faster than the second one, okay? So I'm going to rewrite them, okay? So what's going on here is that you start from your reactant A, okay, your fuel, for example, and very rapidly this is going to be depleted. You see here, A is going to be depleted with a time scale, which is a very fast time scale. Okay? We have here what is called, I'm going to write it here, a temporal boundary layer. You're used to hearing about boundary layers in wall-bounded flows, okay, where you have essentially a very thin layer where the velocity, okay, will go from the bulk velocity to 0, okay, in a flow which is near a wall, okay, because you have no slip conditions at the wall, okay, in viscous flows, okay, where you have a finite Reynolds number, okay. You probably remember this from your gas dynamics or aerodynamics knowledge, let's say. Now, as a temporal, okay, parallel, we can say that this thin layer, okay, is a boundary layer, a temporal boundary layer. And in fact, there is a reason why we say boundary layer, okay, because, and we'll talk about it later on, but you can actually do a parallel, okay, with the spatial boundary layer in Navier-Stokes equations, okay? And so very rapidly you have A that depletes, okay, and B, okay, is being formed very rapidly as well, okay? And we say that this is the radical pool, okay? So the intermediates form this sort of radical pool here. And then what happens is that the second reaction, okay, starts dominating, okay? And you see that now the evolution is much slower, okay? And it's evolves on this time scale here, okay? Which represents essentially the asymptotic behavior, okay? By asymptotic, I mean when t goes to infinity, okay? So we can call this, well, in the jargon here, this is called outer solution, simply because we are outside of the temporal boundary layer, okay? And then eventually, when the time scale 1 over K2, the slow time scale, is depleted, essentially everything stops, in the sense that now the radical pool, the intermediate radical pool, is depleted, and we have the formation finally of our product. So this is a long story to say that, generally speaking, in combustion reactions, you have a multiplicity of timescales, and you have a separation of timescales, okay? You have essentially intermediate reactions that are generally intermediate reactions and what we call here initiation reactions, like A going to B, that are very fast, okay? And then terminating reactions, which deplete these intermediate radicals, okay, into and oxidize them into products that are generally slower, okay? So you have a dichotomy here between very fast timescales and slow timescales, okay? Which is the most important message that we have to learn today, essentially. Now, by slow and fast in real life, when you actually measure those timescales, they will span several orders of magnitude. So when you have a complex combustion reaction, you will find scales or timescales ranging or embracing maybe 6 or 7 or even 8 orders of magnitude. So if you have, say, the slow timescale evolving on the order of 1 second, okay? The very fast timescale related to the temporal boundary layer, for example, the shortest timescale will be 10 to the minus 7 or 10 to the minus 8, okay? Which is, by the way, a very, very sort of big obstacle for numerical integration. Go back to your knowledge of numerical analysis. You may remember that if you want to integrate numerically a set of ordinary differential equations, you have many options. The simplest one being Euler, okay, scheme. So it's an explicit scheme, okay? First order explicit scheme. If you have a set of timescales which go from very slow to very, very fast, okay? In order for your scheme, your explicit scheme to actually converge and be stable, you need to take your delta t of the order, so your discrete increment of time, of the order of the smallest, okay, timescale. So that means that in order to integrate the whole phenomenon, embracing all of the timescales, including the slowest one, so up to, say, 1 second, you need 10 to the 7 or 10 to the 8 internal time steps, okay? So that we can actually follow the evolution of all the phenomena involved, okay? Including, by the way, the evolution of the fastest species, okay? In this case, it would be A. Okay, now clearly in this particular system, we only have 2 timescale, 1 over k1 and 1 over k2. In reality, you're going to have, let's say, a spectrum of timescales. Okay, but the important thing is that these models, okay, will help us understand the fact that there is a separation of timescales, and this is the most important message. And also the most important source of, let's say, difficulty in trying to integrate these systems. Okay. Now, how can we highlight this even further? Okay. Now we've seen A going to B and B going to C, and we've seen the differential system that has an analytical solution. We know everything, okay? Now, I would like to illustrate this even further by introducing a concept which goes under the name of singularly perturbed form, okay, of the ordinary differential equation system. Okay. So what we want to do here is highlight, okay, make it clear, okay, that there is a separation of timescales. Okay. So to study the class of systems that have a separation of timescales, we can, if it's possible, okay, rewrite them, okay, in this singularly perturbed form. So long story short, we will non-dimensionalize them, okay? The casting into the singularly perturbed form means essentially non-dimensionalizing the system that we just saw, but clearly you can also do it for other systems. Generally speaking, for very, very small systems, or so-called toy systems that are 2 or 3 dimensional, okay, you're not going to obviously do this for a complete system because it's a paper and pencil technique, so you won't be able to do it with 1,000 species, okay? But for example, for 2 species, it's very handy because we can sort of, it opens up a lot of, let's say, concepts, okay, that will help us understand. So it's essentially a non-dimensionalization. So I'll write it here, non-dimensionalization. So we introduce non-dimensional variables. For example, okay, in place of the concentration of A, we write down small a here, which is essentially A divided by A0. Okay, so this is a non-dimensional constant variable, sorry, with no units. Okay. Now there is no easy way, okay, of casting the original system in the singularly perturbed form. You need a little bit of experience. Okay. For B, we can use the following, okay? We can still use A0, okay, as a reference. We can't use B0 because generally speaking, B0 is 0, okay? The initial value of B is usually 0, so we can't non-dimensionalize with respect to B0. So we'll still non-dimensionalize with respect to A0, okay? And we'll add also here a factor, K2 over K1, which is non-dimensional, okay? And it's a ratio, okay, essentially of timescales. So we introduce a ratio of timescales here, okay? So let's go back to the original system. If we substitute for A, for example, small a times A0, we're going to end up with this very simple ODE. And for B, we're going to have essentially K1 over K2 dB by dt equals K1A. So we're just non-dimensionalizing. It's very, very straightforward. B, K1 over K2. Okay, so this cancels. Okay, so we have essentially K1 A minus B. Now, this is not fully non-dimensionalized, clearly, because we still have time. Time is dimensional in this in these equations. So we introduce a non-dimensional time t, which would be K2 times t. Remember that K2, okay, just as much as K1 has units of 1 over time. So tau now becomes non-dimensional, okay? So we have our final form, which is dA over d tau, which will be equal to minus K1 over K2A, okay? And we will define this as 1 over epsilon with the minus sign. All right, let me write this a little better. So minus 1 over epsilon, okay, A, okay? And dB by d tau is simply A minus B. So we didn't do anything to the system, okay, other than using these, okay, non-dimensionalization rules to rewrite the system. So it's the same system in this particular form, okay? Where now epsilon is what? Is K2 over K1, okay? So remember that we said that K2, actually K1 is much bigger than K2, okay? So what is the meaning of epsilon, okay? Well, we can write it as 1 over K1 over 1 over K2. So now what we're doing is we are comparing timescales. Remember, K1 was much bigger than K2, so 1 over K1 is very small. So this would be the fast timescale, okay? And at the bottom, we have a slow timescale, okay? So you can see that, which is, now clearly, the fast timescale is of order epsilon, and the slow timescale is of order 1, okay? So clearly, this is a much smaller than 1 number, epsilon. So let's go back to here, okay? To our singularly, this is what we call by singularly perturbed form, let's say, of our system, okay? We have non-dimensionalized it fully, and what we have done is we have highlighted here, okay, a small number which is representative of the ratio of the fast to the slow timescales, okay? You may ask, okay, but what's the advantage of this? Well, slowly we'll see what the advantage of this is. First of all, we have essentially deprived the system of all the constants, okay? And we have absorbed all of the constants into this epsilon, okay? Which contains now very physically meaningful objects which represent timescales. So epsilon represents a ratio of timescales. So again, I mean, if you have a separation of timescales where you have a very short and a very long timescale, this is the ratio, okay? Epsilon. And it's a small number. That's why we call it epsilon, by the way. Okay? So let's write it here. Epsilon is a small number. Okay? Now, one thing that you can actually see, being epsilon very small, is that, well, the absolute value of the rate of change of dA by d tau is much larger than dB by d tau. Okay? So dB by d tau will be order 1, and dA by d tau will be of order 1 over epsilon, which is large, clearly, because epsilon is much smaller than 1. What does that mean? Well, it means essentially that A now becomes a fast species, clearly, because it evolves, okay? Its rate of change, dA by dt, is very large. And we will call then, by contrast, B is slow species, okay? So again, we wrote down this equivalent system by defining now A as a fast species and B as a slow species, okay? Very good. Now, again, I mean, there is nothing special about this other than it's a non-dimensional system. Now, you can write for this an analytical solution. Let me write it over here, okay? A, it's still a linear system, okay? So will be A0, okay? E to the minus tau over epsilon, okay? A0, by the way, is simply 1 because it's the molar concentration of A divided by the initial. And B, we can write it as epsilon minus 1. Okay, this is the complete form, okay? A0, and then you'll see the two time scales here, minus tau, so a time scale of order 1, okay, minus e to the minus tau over epsilon, okay? So clearly now, because it's divided by epsilon, which is a large, 1 over epsilon is a large number, this will go to 0 asymptotically, or very fast, okay? And we have implicitly said that B0 is 0, okay? But that doesn't really make too much difference, okay? So again, if we are to draw this system, okay, the evolution, we'll have a very, very fast sort of evolution here, which is within the boundary layers, and so it's order epsilon, where you have essentially the exponential decay of A tau, okay, this is tau. And then you have a much sort of slower evolution here, okay, with B of tau, which eventually or evolves on this much smaller time scale. Now, of course, just as before, we have B initially growing and then being sort of constrained on this evolution here. Of course, you shouldn't be drawing the little squiggles here. You should go straight, obviously, but I can't. So, okay. So again, you can see a temporal boundary layer here, okay, very short, and then the asymptotic solution, which is the outer solution, okay. Now, the handy or quite useful reason why, or aspect, let's say, of singularly perturbed forms, okay, like this, is that now we can recast it, for example, in this form, okay? Sorry, minus A and dB by d tau equals to A minus B. Okay, so this is our singularly perturbed form. I just place this guy here, epsilon, on the other side. Okay. Now, as we usually do, why not now take epsilon and shrink it to 0? Okay. Now, what does that mean? Well, if we look at this picture here, you can still hear me, right? Don't let me talk by myself.
Yes, Prof.
Okay, I hope it's what I'm doing is quite clear here. So of course, because I cannot use I don't have the privilege of using my mouse here, I always have to draw these stupid arrows. But look at this picture here. We have a very short temporal boundary layer, okay? Now, I can make it whatever size I want because it's epsilon, it's a free parameter. And we know that epsilon is very small. So we may as well do something. We may as well just shrink to 0, okay, this temporal boundary layer. What does that mean? It means essentially that I'm contracting to 0 the fast time scale, okay? So the fast timescale now becomes instantaneous, okay? Instantaneously or infinitely fast. What we're doing here by shrinking this to 0 is that we're actually highlighting this behavior here, okay? The slow one, the asymptotic behavior. Okay? So let's see what happens to our system, okay? We shrink epsilon to 0, and what we have here essentially is, well, the first term here will be 0 equals to minus a. So we have a first result, which seems pretty obvious, okay, that a differential equation of first order, an order differential equation, now becomes an algebraic equation, or if you will, an algebraic constraint. On the other hand, the second term, the second equation, dB by dt, okay, is equal to, well, nothing really special happens to it other than we know that now a is equal to 0, so we can write down a minus b equals 0 minus b. Okay, so in fact it's minus b. Okay, so now it may seem obvious visually, but in fact we've done a rather important operation here. Well, first of all, we've operated a reduction of complexity of the system by shrinking epsilon to 0, so driving the fast scales to be infinitely fast. We have reduced the order of the system from 2 ODEs, okay, to 1 algebraic equation, okay. You can write. I'm shortening it to algebraic constraint or equation. This is it. 0 equals a, plus only 1 ODE. Not only that, but up here you had 2 timescales. How many timescales do I have here? Only 1. In fact, I only have the slow one, the order 1 timescale, the asymptotic behavior, the order 1 timescale. Okay, epsilon has disappeared. Okay. Now let me introduce some notation here. This algebraic constraint, we will look at it more specifically later on. I am giving it the name M0, okay? And I'm going to call it the, well, reduced, you can even neglect, okay, this terminology. What's important is slow manifold. Okay, we'll see what this means in a second. It's a constraint. In fact, it's a graph, okay, in space, in the phase space AB. Okay, this is our phase space, okay, where you have axes for each species, okay? And what's this? Well, this will be a slow evolution. It's actually very simple. B, okay, of t will be equal to some initial value. Let's call it b prime because it's not going to be 0, obviously. Okay, it's going to be probably the value attained here. Okay, but most importantly, which evolves on the slow time scale. Okay, e to the minus tau divided by 1. Okay, so essentially the time scale is order 1. So you see what happens by just reducing the system and taking epsilon to 0, we have essentially reduced the system in complexity. We have eliminated one of the 2 timescales, okay? In fact, the fast one, and we have reduced also the dimensionality of the system to essentially only one ordinary differential equation plus one algebraic constraint. Now, you may not know this, but you've already done this many times, okay? In all sorts of aspects of physics, you have equations that have essentially small numbers multiplying terms in your equations. I will give you one example that will also explain why the fast timescale is called a boundary layer. Go back to your fluid dynamics notions, okay? For those of you who've done fluid dynamics. Navier-Stokes equation. Navier-Stokes equations mathematically is what? It's a partial differential equation of order 2, right? Because you have the highest order of the derivative is in fact is a Laplacian, is a second order differential, okay? I hope you remember that. So it's something like this, okay? Where u is your velocity. And if you remember, if you non-dimensionalize your system, this viscous term is multiplied by 1 over the Reynolds number. I won't write down the full equations. It's meaningless. The other equation, the others are essentially the convection term is a first order nonlinear, okay, term. First order differential, okay, term. But you have the viscous term is actually, so this is essentially viscosity, effective viscosity is multiplied by 1 over the Reynolds number, right? Now, one over the Reynolds number is very similar to, essentially, having an epsilon, right? Especially when the Reynolds number is very high, okay? So in fact, suppose that we implement the position Reynolds going to infinity, okay? Well, we have, for all intents and purposes, a non-viscous fluid, okay? So we have viscosity playing no role, okay, with respect to convection. So this term here, in fact, tends to disappear from your equations, okay? So you see that now your equations become, from second order, they become first order. We call them the Euler equations. And the boundary condition, sorry, the boundary layer essentially disappears, right? It shrinks to 0. It's exactly like we're doing here on a temporal basis, okay? This is not clearly the only parallel that we can make. There are all sorts of other systems that can be approached, okay, with this technique, okay? So I hope you can see the parallel here, okay, with the fluid dynamics. Here, of course, we're talking about time, okay? There is no space. We're talking about time, but we're still essentially referring to this very small evolution, which was a boundary layer and a spatial boundary layer in fluid dynamics next to a wall. Now we're actually referring to in terms of time, or temporal evolution, okay? So what happens if we shrink to 0? But let's get rid of this. If we shrink to 0, the temporal boundary layer, I'll just put it down here, okay? Well, you have that this will be essentially shrunk to 0. So what you have essentially is the very slow evolution, okay, of order 1 evolution of B, okay, which is here. This is your B prime 0, okay? So B0 prime e to the minus tau. This is clearly tau, okay? And A, what happens to A? Well, A of tau is simply 0, Okay, so A will be constrained on this axis. And in fact, we called this M0, the slow manifold. Okay. Now, in theory, you could do also the opposite. Okay. Think about this. Suppose that instead of highlighting the asymptotic behavior, I want to highlight what happens in the boundary layer. Okay, I want to expand the boundary layer. Okay, what can I do? Well, I have to somehow operate a dilation in time. So suppose that I introduce a new time variable t prime, which is tau divided by epsilon. Okay. Now, if you now take epsilon to 0, what you're actually doing is you're expanding time infinitely. So if in this case here, okay, we are shrinking to 0, okay, the fast timescales, okay, so we make the fast timescales instantaneous. With this position here, what we can do is, okay, we essentially freeze the slow timescales. They're so slow that they're frozen in time, okay? And the fast timescales now become the slow timescale, okay? So I'm just playing around with these timescales, okay? So I make a sort of a dilation in time. So now I have my system, okay, which is of this form here, okay? And now dB over dt prime is epsilon a minus b, okay? So if I now do exactly the same as before, okay, I tend epsilon to 0, you will have essentially, well, nothing happens to the first one. So now A evolves on a time scale minus t prime here, and dB by dt will be essentially 0. So B will be frozen. Okay, the slow time scale on which B was evolving is now so slow that it's frozen in time. So you will have essentially a very large boundary layer where B is essentially frozen. Okay, this is supposed to be a horizontal line. Oh my God. So that's B0 prime, which is constant. Okay, and A will essentially decay to 0 within your boundary layer. Okay. Now, another way of looking at this. Oh, and by the way, if we had called the slow manifold, okay, the algebraic constraint here, okay, for the asymptotic behavior in the boundary layer, we're going to call these the so-called fast fibers. Okay, it's essentially the constraint, the algebraic constraint that we have within the boundary layer. So, long story short, suppose that I now revert to my phase space A and B. Okay. Well, let's look at this situation. Ooh, sorry. Let's look at the first system here. okay, the asymptotic solution, okay, we have A equals 0 is my slow manifold. So this line here, A equals 0, is my slow manifold. So on this line, okay, I'm going to have my slow evolution, okay, of B, okay, slowly decaying towards 0, okay, with a time scale of order 1. On the other hand, the fast fibers are B equals constant. So these are these lines here. So these are the fast fibers, depending on what value of B0 is. So in fact, you have essentially, you see a very fast evolution here, and then a very slow evolution here. Fast evolution here and a slow evolution here. So what we're actually doing, basically, is trying to, so this is time scale, let's say, of order epsilon, where our system decays onto the slow manifold, and then here we have a time scale of order 1. What we've done is we've taken essentially, now I'll stop here, so try to sort of imagine it a little bit in general. I've taken this dynamics, which I know is fast-slow dynamics, okay, and I'm trying now geometrically to give it a backbone, okay, a sort of a constraint, both in the fast time scale, but most importantly in the slow time scale, in the evolution. So you see this line A0 here, A equals 0, represent an attractor, okay? It's called a manifold, okay, but it attracts all the trajectories of the systems, okay, depending on whether the initial condition is, depending on where the initial condition is, it will attract all the asymptotic behavior of the system. And in fact, on that manifold, which is a constraint for the system, okay, only the slow timescales will, in fact, be present. We'll see later on that this is very important. It will mean a reduction of a system in complexity, okay, and also reduction in stiffness. Stiffness is when you have separate timescales which are farther apart. On M0, you only have one timescale of order 1, okay? So I know it's a little bit advanced as a concept. Some of you may have seen it right away. Some of you may need more examples, which I'm going to give you later on. So next time I'm going to give you, we're going to go back a little bit to linear systems, and then we're going to do a parallel to nonlinear systems, and you'll see that it's a concept that you'll familiarize with, okay? This singularly perturbed form of nonlinear systems, okay? For the time being, sorry, I stole a few minutes off of your time. We can stop it here.